Hi, welcome to lesson 7.1, Angles of Polygons. In order to prepare for chapter 7, please make sure you tear out pages 195 all the way through page 220. Pause the video and make sure you tear out the whole page. Once again, it's pages 195 through 220. Make sure you staple them together and put your name on it. Okay. Before we start with the exploration, we need to make sure that we write down where the problems are going to go. So please turn to page 197. Okay, so on page 197, you are going to do problems number 1, number 2, divide that into two parts. Problems 3 and problem number 4. On page 198, you're going to do problems 5 and 6, and we're going to do a proof right there. This is on page 198. So pause the video and go back and make sure you put these numbers so that you know where the problems go. Now, let's go back to the exploration. What you guys see right here is an example of two types of polygons. A quadrilateral that has a total of 4 sides, and you have a pentagon that has a total of 5 sides. And let's not forget here that n represents the number of sides in a polygon. Okay, so for example, a quadrilateral has 4 sides, a pentagon has 5 sides. So what we're going to do is we're going to look at a figure that has 3 sides. And now we all know that is exactly going to be a triangle. Now, we have talked about triangles in the past. We know that the sum of the angles in a triangle is exactly 180 degrees. Now, that is based on the number of triangles that you can create with a triangle. So the triangle is already a triangle. But if you look at this, for example, you can create 2 distinct triangles here. The sum of all these angles is going to equal 180 multiplied by 2. And in this case, 180 times 1. Now, I can create, without the diagonals crossing each other, this pentagon, you can create 3 different types of triangles. So the sum of the angles in there is going to be 180 times 3. Now, what if you have a hexagon? A hexagon has 6 sides. So 1, 2, 3, 4, 5, and 6. They don't have to be equilateral or equiangular, and I'm going to explain what those mean in just a bit. So here is a hexagon. Hexagon. All right. It has 1, 2, 3, 4, 5, 6 sides. So how many triangles can I come up with? In this case, 4. So the sum of the interior angles of this polygon is 180 times 4. So now my question is, what would the sum of the angles be for example, I don't know, a polygon that has 172 sides? Well, we need to start looking for a pattern here. Okay, what will be the pattern between 3, 1, 4, 2, 5, 3, and 6, 4. You notice that this number is always 2 less than the number of sides. So if I really want to figure out what the sum of the angles in a polygon is going to be, all I need to do is multiply it by 180, multiplied by the number of sides, subtract 2. So in this case, whatever 180 times 170 is going to be the sum of the angles in a polygon that have 172 sides. So in this case, I have my calculator handy right there. Okay, the sum of the angles is going to be 30,600. Now we can do this with any polygon that has 3 or more sides. So in general, if I wanted to develop an equation for this, if I had a polygon with, say, n sides, what would the sum of the angles be? Well, it would be very simple. 180 multiplied by the number of sides, subtract 2. Okay, so this equation right here, okay, that we are using, this one right there, 180 times n minus 2, this represents the sum of the interior angles of a convex, I'll explain what that is in just a second, a convex polygon. Okay, the word convex is very, very important. So what is a convex and what is not a convex? In a convex polygon, you can draw diagonals, and the diagonals will remain on the inside of the polygon. So for example, let's look at the difference between convex and what is not a convex, which is called a concave. So in a convex polygon, okay, you can draw your diagonals, meaning from one vertex to any vertex, and all of them, regardless of where you put them, they're all going to be inside the polygon. However, if you have a polygon that looks like this, okay, believe it or not, that is a polygon, but it's a concave polygon. Now, why is it a concave polygon? Because look, the segment joining two vertices lies on the inside and on the outside, and even in this problem right here, it could be partially inside, partially outside. So these are all examples of concave polygons. So this equation right here only works for convex polygons. So now let's turn to page 196. Now on page 196, we're going to start talking about what exactly is a regular polygon. Okay, so not all polygons are considered regular. A regular polygon has two main characteristics. Okay, the first characteristic is that it's equilateral, and the second one is equiangular. So let's write that down. Okay, a regular polygon has two characteristics. One, it is equilateral, and equiangular. So what does that mean? It means that all the sides of the polygon are congruent. So all sides are congruent. Equiangular, all angles are congruent. A perfect example of this would be, for example, the equilateral triangle or the square. Okay, so my question is, how can I find what one of these interior angles is going to be? Well, we're going to use the equation that we just figured out from the previous page. 180 times n minus 2 gives me the sum of all the angles, but all the angles are the same, and it corresponds to the same number of sides. If you have, for example, 5 angles, then you have 5 sides. So in order to figure out what one of these angles is, you have to divide this by the number of sides. So this is the measure of one interior angle. And we're going to use this equation to in several applications. All right, so let's go ahead and turn really quickly to page 197. Now, this is the theorem that we just came up with. It's called the polygon interior angle theorem. The sum of the measures of the interior angles of a convex n-gon. People get confused with an n-gon. What does an n-gon mean? So we have a specific name for a 3-gon, which is a triangle. A 4-gon is a quadrilateral. A 5-gon is a pentagon. A 6-gon is a hexagon, and so on. An n-gon really represents any figure that has n as the number of sides. Now, they like using n minus 2 times 180. I like doing 180 times n minus 2. It's the same exact thing. It's just a matter of personal choice. I like this instead. Okay, so that's called the polygon interior angle theorem. So let's turn to page 198 in your journal. And let's take a look at two things, the corollary and the next theorem. All right, so the sum of the measures of the interior polygon of a quadrilateral is 360. And if I were asked to prove this, this would really be super simple because a quadrilateral has 4 sides. So all I would need to do is put the 4 into the equation for 180 times n minus 2, n being 4. So that gives me 180 times 2, which is indeed going to be 300. So if they wanted me to prove this, this would be my go-to plan. Now the next one is a little bit more complicated to explain. So I want you to pay very, very close attention. It says the sum of the measures of the exterior angles. Notice that they're talking about the exterior angles, not the interior. Okay, of a convex polygon. Okay, one angle at each vertex is 360. So here's an example of a 5-sided polygon. Now what happened is that we extended all the sides to get all the exterior angles. And what we're going to try to show here is that the sum of all the angles is 360. Now here's the thing. You could really do this with any polygon with n number of sides. Okay, so I'm going to show you just a very quick example of what one of those might look like. Okay, so if I were to do the exterior angles for all of these, notice that I did not enclose this polygon because my polygon here has a total of n sides. So it's an n-gon. Now, if I were to name these exterior angles, for example, angle 1, angle 2, angle 3, angle 4, and so on. The last one, of course, is going to be n. That's going to be the last angle. All right. So my question is, what are the interior angles then? If this right here is angle 1, then this angle right there is 180 minus the measure of angle 1. So this is going to be 180 minus the measure of angle 1. All right. This angle here would be 180 minus the measure of angle 2. This angle here would be 180 minus the measure of angle 3, and so on. So all I know is that the sum of all those angles is going to be, 180 times n minus 2. We know that already. So let's go ahead and start, adding those. So for example, the first angle is going to be 180 minus the measure of angle 1 plus 180 minus the measure of angle 2 plus 180 minus the measure of angle 3. And of course, there's a bunch of them in the middle that we do not know. But I do know that the last one is 180 minus the measure of angle n. But here's the thing. I know what the sum of this is going to be. These are all interior angles. Therefore, the sum, and I know it's going to be kind of small here, it's going to be 180 times n minus 2. So we know that already. So now we just got to work with all of this. Okay? So this is really, really simple because you have 180, 180, 180, 180. How many of these 180s do you really have? You have n of them. So all of these right here, okay, they're all going to combine together and give me 180n. Okay? Now, here's the thing. I have minus measure of angle 1, minus measure of angle 2, minus measure of angle 3, minus measure of angle, and like all of them together. So what I'm going to do in this part is I am going to put them all in a parentheses. But because I'm putting them all in parentheses, all these minus signs are going to turn to addition. So the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 plus dot, 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 all of them, plus the measure of the last angle. And that's going to equal 180 times n minus 2, of which if I were to distribute, I would get 180 n minus 360. Now I want you to notice one thing. You have 180n on both sides, so you can actually subtract them and those are gone. So what are you left with? You're left with a negative. Now believe it or not, there's a negative 1 right there. You're left with negative 1 times the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 plus the measure of angle n equal to negative 360. If I multiply both sides by negative 1, those are gone. So we end up with the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 dot, 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 plus the measure of angle n equals 360. But what does all of this right here represent? Okay, they represent the exterior angles, the sum of the exterior angles. So here we just proved that the sum of the exterior angles is 360. Now this was more like an algebraic proof, not a 2-column proof. If we wanted to put this in a 2-column proof, we could, but we're not going to do so. This is more like a paragraph proof, you would say. All right, so now we are ready to begin our examples. Okay, please make sure you wrote down where the examples go. If not, here they are again. On page 197, problems 1 and 2 go there. Problems 3 and 4 go there. And on page 198, 5 and 6 go right there. So let's go ahead and begin our examples. All right, here's example number 1. Okay, let me center this a little bit. All right, it says find the sum of the measures of the interior angles of the figure. So the first thing we need to look for is how many sides do we have? Okay, let me zoom in a little bit more. All right, much better. All right, so looking at this diagram right here, I have 1, 2, 3, 4, 5, 6, 7, 8 sides. So I have a total of 8 sides. Now the equation for the sum of the interior angles of a polygon, which is on page 197, okay, the polygon interior angle theorem is 180 multiplied by n minus 2. N represents 8. So all we need to do is simply substitute the 8, and that's going to give me 180 times 6. So you have your calculator handy. If you want to multiply this in your head, go for it. So the sum of the angles in this polygon is 1080 degrees. So if I were to add up all these angles right here, you would get 1080 degrees. All right, that's example number 1. Let's look at example number 2. Okay, in example number 2, they tell me what the sum of the measures of the interior angles of a convex polygon is, and it's 900. And they want me to classify it. So in order to classify it, I need to know how many sides there are. So let's look at the equation for the sum of the interior angles. That's 180 times n minus 2. And that should equal, according to this, 900. So I could do this 2 different ways. I could distribute and solve this as a 2-step equation, or I can simply get rid of the 180 by dividing it, and I get 900 divided by 180, which is 5. So n minus 2 is equal to 5. So what we're going to do is we're going to add 2 to both sides, and you get n equals 7. So this polygon has 7 sides. And a polygon that has 7 sides is called a heptagon. Now, if you don't know the names of some of these, it's okay. Google is free. They're in there. So this is example number 2. Let's look at example number 3. Okay, in example number 3, let me zoom in a little bit. It says find the value of x for the diagram. Now, for this problem, we're going to use the corollary to the polygon interior angle theorem that states that the sum of the angles of a quadrilateral is 360. So here, x plus 59 plus 121 plus 108 equals 360. But say, for example, what if I did not know that it was 360? What could I have done? Well, you see you have 4 sides. So what you could have done is 180 times 4 minus 2, and that would have given you 180 times 2, which is 360. Then you know what you're going to put there, just in case you have a different type of polygon. So now I get to combine my like terms, which is 59 plus 121 plus 108, and I get 288. And that's equal to 360. So to solve for x, you have to subtract that from 360. And when you subtract that, you should get 72 degrees. So the value of x in this case is 72 degrees. All right, let's take a look at the next problem. All right, let's take a look at example number 4. It says a home plate for a baseball field is shown. Is the polygon regular? Okay, so one of the things that you can look at is the fact that you have 3 right angles and 2 angles that are not right angles. So in order for a polygon to be regular, okay, it needs to be equilateral and equiangular. It has to be both. If it does not satisfy either one of those two, then it's not going to be regular. So in this case, all 5 of the angles are not the same. So therefore, it is not a regular polygon. Okay, so for A, you can just say that it is not a regular polygon. And Y, you can just say that it is not equiangular. It is not equiangular. Now it says find the measure of angles C and E. Now C and E, they're both congruent. So my first question is, what does the sum of all the angles have to be? So I'm going to use my 180 times n minus 2. And in this case, because it's a pentagon, has 5 sides, n is 5. So 180 times 5 minus 2 which is going to be 3 times 180, and that's going to be 540. Now that's the sum of the angles. Now according to what we see in this diagram, you have 3 right angles. 90 plus 90 plus 90, that's 270. Plus, now here's the thing. C and E, they both have the same angle measurement. So say I call this one angle X and this one definitely going to have to be angle X too. So the sum of those two is simply 2x. So my goal now is to solve for this. So 270, you're going to subtract it from both sides and get 540 minus 270, and that gives you, again, 270. You divide both sides by 2, and that gives you x equal to 135. So both the measure of angle C and the measure of angle E equals 135 degrees. And that is example number 4. Let's take a look at example number 5 now. Okay, so for example number 5, it says find the value of x in the diagram. Now, we have to remember the theorem that we just learned. The polygon exterior angle theorem states that the sum of the exterior angles, no matter how many sides it has, is going to be 360. So 2x plus 89 plus 67 plus x equals 360. So what we're going to do is combine the like terms. That's going to give me 89 plus 67, which is 156. Divide both sides by 3, and you get x is equal to 52. Now, if they wanted me to go back and find out the angle numbers, the angles right here, all you got to do is just plug it in here. So x equals 52. We just need to remember that the sum of the exterior angles will always be 360, no matter how many sides it has. So that's example number 5. Let's look at example number 6. Okay, so in this example number 6, it says the trampoline shown is shaped like a dodecagon. Find the measure of each interior angle and find the measure of the exterior angle. So there's different ways that you can do this. You can actually do the following. Okay, you can find the sum of all the angles on the inside to be 180 times n minus 2. Now a dodecagon has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 sides. So n equals 12. Okay, that gives you 180 times 10, which is 1800. Now that's the sum of all the angles. If I want to find out what one interior angle is going to be, I have to divide this by the number of sides, which in this case is 12. So 1800 divided by 12 is going to give you 150. So the interior angle is 150. So what does the exterior have to be? Well, remember that the exterior and the interior, they're actually a linear pair. If you zoom into one of these right here, you can see that the interior and the exterior are a linear pair. So the exterior one would have to be 180 minus 150, which is 30. So the exterior angle would have to be 30. Now this is one way of doing this. Oops, sorry, I didn't show that. That's one way of doing this. Another way you could have done and found this one is, you know, the sum of the exterior angles is 360. Divide that by the number of sides and get 360 divided by 12 to give you exactly 30. So since you know that it's a linear pair with the interior, all you have to do is 180 minus 30 and you get 150. So as you can see, there are two different ways to do this problem. And this concludes lesson 7.1. Thank you for watching.